Hello and good afternoon, or maybe good morning, depending on where you are. I'm located in New Zealand, so the time here is 4 p.m. So welcome to this Allied Telesis webinar on basic networking concepts. So my name's Garth Lowe, and I'm a network engineer, and I'm working in the CSG department. So there's the customer service group. So the CSG department, we provide support to our engineers and salespeople around the world. So here in Allied Telesis, we have a very flat support structure. So when a country engineer or salesperson has a problem or a query or whatever, they can contact our APAC TAC. So APAC TAC is our Asia Pacific Technical Assistance Center. And APAC TAC, they support solely to APAC engineers and salespeople. So CSG and TAC, we operate very closely together. We're actually located in the same building and we sit beside each other. And both of us, both of our groups, we have access into our software developers. And our software developers, they're the ones who code our operating system. So these developers will specialize in various protocols and technologies, such as OSPF, RIP, or Rapid Spanning Tree. This means we can provide easy support or easy access. So it means that our country engineers and salespeople, they've got easy access to expertise, and it really shortens our resolution times. Throughout this webinar, if you've got any questions, you can just ask in the Q&A chat bubble, and someone will answer your question. So who is Allied Telesis? So I'll just give you a brief rundown on who we are, our offices, and what we do. So Allied Telesis was founded in 1987. We've been serving the needs of our network communication industry for over 30 years, focusing on connecting people through networking. Our headquarters is in Tokyo, Japan. We have around 3,000 employees in 56 locations worldwide. We have 7 R&D centers. We own 3 manufacturing factories in China and Singapore. Our head office oversees the operation of the factories from production lines to sales and support, including precise product control. This means we are committed to provide our customers with products designed and built to the highest standards and quality. We provide everything from product planning to development, from development to manufacturing, and from manufacturing to evaluation and world-class professional support. Allied Wear Plus, Vista Manager, and AMF, our AWC Smart Connect and Channel Blanket, all this works together as an extremely powerful network monitoring and management, connecting the world securely and safely. Our world is increasing in complexity. Our goal is to make complex networking simple, secure, cost-effective, and manageable. Today, more than any other time, you need a technology partner that has both the vision and the capability to take your computer communications to where you need them to be. So that was just a little bit of an introduction to who we are. So this webinar will be focusing on these topics here. So switching and routing. So what is switching and what is routing? We'll look at some commonly deployed topologies in today's networks. And we'll look at some features that will make networking more robust and more redundant. We'll have a look at some network management, and then we'll look at some products that we can use in these sort of network topologies. So switching and routing. So there are two types of switches. We've got a layer 2 switch and a layer 3 switch. So layer 2 switch, it operates at the data link layer. So in the last webinar, we had a look at the OSI model and we had these different layers. So we had the data link layer and also the network layer. So layer 2 switches operate at the data link layer. So that means they operate in the Ethernet space. So layer 2 switches only understand about Ethernet. On the other hand, layer 3 switches, they operate in the layer 3 space. So they understand about IP. They also do understand about layer 2. So the difference is the layer 2 switch can only switch packets based on the MAC address because that's what they operate in. A layer 3 switch, they route packets based on the IP address. So within layer 2, we've got two types of switches. We've got intelligent switches and non-intelligent switches. So in other words, intelligent switches are just managed switches. And non-intelligent switches are unmanaged switches. So an unmanaged switch is basically, we can't configure any features on them. Basically what you do is you unpack the switch out of the box and you just plug the switch in, connect it all up, and it just works. With intelligent switches or managed switches, what we can do is we can program it with various features, and these features can make the network more robust and more redundant. And we can also pull things, statistics from the switch. So we can see, if a port is up or down. We could see, how much traffic is going over the port. We can have a look at how busy the CPU is, the fan speed. So one of these features is SNMP. So SNMP is a network management protocol, and it allows us to pull that information, like is the port up or down. With a non-intelligent switch or unmanaged switch, you can't pull that information. So a layer 3 switch is always managed. So you always have to configure a layer 3 switch. So because it operates in the IP space, you need to configure the networks it knows about, so the IP networks it knows about. And then what it will do is it then route between those IP networks. The other thing is if you the layer 3 switch can also operate as a layer 2 switch. So you can just unplug or unpack the layer 3 switch, install it in the network, and it will just operate as a layer 2 switch. It won't do any routing because you will need to configure it. So this slide here just compares what a router and a layer 3 switch is. So in terms of functions, a layer 3 switch and a router, they perform exactly the same functions. They route packets. The only difference is where they're deployed in the network. A router is normally deployed in between your LAN and your WAN, in this case here, the internet. Whereas a layer 3 switch, it's normally deployed just in the LAN environment. There are some other differences, but you have to remember both a router and layer 3 switch, they do the same function, so they route packets between networks. So typically on a router, you'll have a small amount of ports. Typically, in this case here, we've only got 6 ports here. On a layer 3 switch, you'll have a large amount of ports, maybe 24, 48 ports. And the reason behind that is where the packets are processed. So on a layer 3 switch, packets are processed in hardware. So on a layer 3 switch, there's actually a dedicated silicon or chip that actually processes the packets. And it's all done in hardware. So a packet comes in, it gets routed by the silicon, and then out it goes. And it's very fast. Whereas a router has to process the packets in the CPU. So, a packet comes in, has to be sent to the CPU has a look at the packet and then may route the packet out. And this is the reason why a router has a low amount of ports, because if you have a lot of ports, then all that traffic has to go to the CPU, and that could be a bottleneck. The other difference between a router and a layer 3 switch is a router has or could have different interfaces. So it could have like an ATM interface, or it could have an ISDN interface, BRI or PRI. Whereas a layer 3 switch, they won't have those types of interfaces. It'd always be internet. These days, typically from your ISP, a lot of times they'll be using Ethernet. So, ATM, BRI, PRI is sort of older technology. And because where they're deployed in the network, they've got a different feature set typically. So because the router is connected to a sort of unsecure network, it needs to have certain features to protect us. So a router will have, firewalls, or have NAT, and it might be able to do VPNs like PVOE. Whereas a layer 3 switch, it doesn't need to worry about those security features. I mean, it still has security features, and it can restrict users on the LAN. But typically, it's got a different feature set. So, we've got VLANs, link aggregation, etc. I mean, I'll talk about VLANs and link aggregation later in the presentation. So we just want to talk quickly about what is switching and what is routing. So switching occurs at the data link layer. So switching occurs on the Ethernet layer. And if we take a step back and look at what there was maybe 20 or 30 years ago, there were these things called hubs. And basically what a hub did is when a packet came into a hub, the hub would transmit that packet out all ports. So this was quite inefficient because obviously that packet is going to a particular device and is not going to other devices. So that bandwidth has been a little bit wasted. So a switch was introduced. So what a switch does is it will only send the packet to the device that requires the packet. It won't send the packet out to any other device. So say PC A here wants to send it to a packet to PC B, but going to the switch would only send it to PC B, and PC C wouldn't receive the packet. So it does that by using a thing called a forwarding database, also known as a MAC address table. Basically what the forwarding database does is it just tells you what devices are connected to a port. So in terms of this little diagram down here, the switch will know that PC A is connected to port 1, PC B is connected to port 3, and PC C is connected to port 5. So this table here is a dynamic table. So the switch learns entries. It learns where the devices are. So it's a dynamic table, like I said. So entries can be added in, and if the entries aren't used, typically after about 5 minutes, those entries will age out and then be deleted. So we'll just step through an example on how this forwarding database is populated. So when you turn on the switch, the forwarding database is empty. There's nothing in it. So it doesn't know where any of the devices are. So in this case here, PCA wants to talk to PCB, so it wants to send a packet to PCB. So what happens is it sends out an Ethernet packet out here, and the switch will receive the packet. The switch will look at the Ethernet source address, so the source MAC address, and note down, oh, I've received the packet from PCA with the MAC address A, and I've received it on port 1. So I'll put an entry saying, yep, PCA belongs to port 1. So at this stage here, because the packet is going to PCB, it looks in the forwarding database and tries to find an entry for PCB, so MAC address B. There won't be an entry in the table. So what the switch will do is, oh, I don't know where PCB is. So because I don't know where it is, I'll send it out all ports. So I'll send it out to PCB and it will send it out to PCC. So when PCC receives the packet, it'll look at the destination MAC address and note, oh, this packet is not for me. So I'll just drop the packet. PCB will receive the packet and then it'll go, oh, this packet's for me. I'll have to respond. So PCB will respond. So this packet is for PCA. So when the switch receives the Ethernet packet, it'll look at the source MAC address and say, oh, okay, I've received a packet from PCB with MAC address B, and I've received it on port 3. So I will now add an entry in the forwarding database to say, off port 3 is MAC address B, which is PCB. We'll then look at the destination MAC address and note it's for PCA. So I'll then look in the forwarding database and it will say, oh, I've got a packet for PCA, so I've got an entry. So I need to send it out port 1. So it will then send it out port 1. So this mechanism occurs on all layer 2 switches, whether they're managed or unmanaged. The only difference is in unmanaged switches, you can't actually see this forwarding database table, but it will reside in the switch. With a managed switch, you can actually log into the switch and you can have a look at this forwarding database and you can see what the switch knows about. So that was switching. So routing operates at the next level up in the OSI model, so the network layer. So it works at the IP layer. So what routing does is it routes packets between networks. So in this example down here, it's a little bit crowded, but what we can see is we can see a bunch of layer 2 switches, and then we've got a layer 3 switch here, and they're actually connected to each of the layer 2 switches. The layer 3 switch is also connected to a router, which is then connected to the internet. So what the layer 3 switch does, when it connects into the layer 2 switches, it actually assigns a network to those layer 2 switches. So those layer 2 switches now belong to a particular network. So we looked in the last webinar about an IP, so we're operating at the IP layer. So an IP address has got a network portion and a host portion. So the layer 3 switch will then assign the network to each of the layer 2 switches. So we can see here in the sales department belongs to 192.168.1 network, and the engineering department belongs to the 192.168.2 network, and the marketing department belongs to 192.168.3 network. So what the layer 3 switch does, it allows packets to then be routed between these networks. So if sales wants to talk to marketing, they'll come in from this network, the layer 3 switch will then route the packet and it will then send it to the marketing network. Likewise, if the sales department wants to talk to the internet, they'll send it to the switch, layer 3 switch, the layer 3 switch will then route it and to the router, and the router will then route it over to the internet. So it makes these decisions based on a routing table. So any device that's doing layer 3 routing has a routing table, and the routing table basically describes what device to send the packet to. It's probably best as an example down here. So what we've got here is host A, and he wants to talk to host B. And host B is on network 4 over here. So he'll send a packet, and he'll have a default gateway, and his default gateway will say send the packet out to router A. So he'll send the packet out to router A. So remember, routers work at the IP layer, so the IP address it will have the network portion and the host portion. So router A will look at the IP address, work out what network it's going to. In this case, it's network 4. So router A will have a routing table, and the routing table is basically a decision tree. So in this case, it's saying, like, to get to network 2, you need to send the packet out to router B. If you're going to network 3 or network 4, you need to send it out router C. In this case, the packet's going to network 4, so it sends it out to router C. So router C will receive the packet. It will look in the routing table and note that the packet is for network 4. I'll say, oh, if you need to go to network 3, oh, I'm connected to network 3, so I can send the packet out directly. But in this case, it's sending it out to network 4. So I need to send it out to router D. So it sends it out to router D. Router D receives the packet. It looks in the packet and it'll notice for network 4, it'll go, oh, I'm connected to network 4. It'll then look at the host portion of the IP address and note that it's for host B. So it will then send the packet directly to host B. So this is a quick summary of how routing occurs. So any layer 3 device will basically has to do this functionality. Whether it's a router or layer 3 switch, it all has to do this. So we'll move on to network topologies. So these days we've got 2 types of topologies that are deployed in networks. We've got a star topology and a ring topology. So a star topology is where you've got a central device and all your other devices connect into that central device. This is kind of a hybrid star because you've got some of these edge devices that are connected to your distribution switch, which then goes to your core. So this core distribution edge is a standard sort of network deployment. So you've got your core switch and your router connects to your core switch, and typically all your servers connect into your core switch. And then you've got your distribution switches, and they feed your edge switches. Your edge switches typically have your users, could have wireless APs, CCTV, cameras, etc. and they feed into your distribution. Distribution typically doesn't have end users, but you could connect end users into your distribution switch if you wanted to. So a ring topology is basically what it says. So the switches are connected up so they form a physical ring. So choosing between the two topologies, it really depends on what your requirements are. And, you need to just examine, where your switches are going to be located, et cetera, et cetera. I guess one of the things about advantages of a ring is that with the star topology, you've got all your switches feeding into, say, the central switch. So if one of these switches is a long, long way away, it means that you will need to, run a fiber cable, and it could be like kilometers away, and it could be a very long run. So with a ring topology, instead of running a very long cable out to one of the edge distribution switches, you can actually run it to an intermediary switch and then link it up to the other distribution switch. So it just shortens the links. So also in here, we've, if you note here, we've got distribution and edge is combined, but you can have some sort of hybrid topology where you could have some separate edge switches and then they feed into the switch here. So this slide probably won't make much sense at the moment. So what we're going to be talking about all these sort of features. So basically, these features here and also here just increase the robustness and redundancy of the network. So you'll notice that, there's a single switch with a single link. So there are points of failure within the network. So, if this link here failed, it means that all these end users down here, they'll lose their network connectivity. And if this switch here should fail, then you've lost your connection to your router and maybe your servers. And likewise here, the ring has got a certain amount of built-in redundancy. So if you lose a link, you've still got a link. But if you lose your core switch, then you've lost your connection to your router and your servers. So so I'll talk about these various different technologies soon. So AMF is our network management framework, and that allows us to manage the network, and it reduces operational costs in terms of time and also sort of resources. So we'll just now go on to some various features. And so these features are more sort of features that will build in robustness and redundancy into the network. So the first one is virtual chassis stacking, or just stacking. Very simple concept. It allows us to join two switches together to form one switch. So when we do that, these two switches operate as one. The way it works is one switch will be the master switch, the other switch will be a member switch. When you log into the switch, the master, you will just see a combined view. So it'll just look like one switch. In terms of operating, the processing is done on the master. And if the master should fail, then the member will take over. By doing this, it allows us to build a bit of redundancy into the network. So you know, if this switch here fails, we've still got this switch here that can then forward the data onto the various servers or whatnot. And you'll notice down here that you've got two links. So one link goes to one switch and the other link goes to the other switch. So it provides a bit of link redundancy. So EPSR, Ethernet Protected Switch Ring, is a ring protocol. And you need to have a ring protocol, otherwise what happens is when you form a ring in the network, what you're doing is you're creating a loop in the network. And when you create a loop in the network, it will bring down the network. Basically what will happen is packets will just loop around, and because it's operating at Ethernet, those packets will always exist. And if it's a broadcast packet, those broadcast packets will be sent out to all devices. So if you've got a lot of broadcast packets, it will just slow down or consume CPU cycles, and it will slow down the device. So EPSR is a protocol that needs to be run to prevent this loop from occurring. A very simple concept. You've got a master, and then you've got all these transit nodes. And what happens is the master will send out a thing called a health message, and this health message will be passed around the ring until it comes back to itself. When it comes back to itself, it knows that the ring is complete, and then it will just block the secondary port. You also note that this is probably not the most optimal position for the master. So if this master here was the core and you had servers and routers plugged into it, it means that devices hanging off this device here, if it needed to talk to, say, a server or go out to the internet, it would have to go through all these other switches before it can egress the network. So in some respects, your master doesn't have to be in the core. We put the master over here. This is still the core. So one of these two ports will be blocked. That means when the users on this switch needs to go and access the servers or internet, it will just go directly to the core switch. So EPSR's failover time is very quick. So in this example here, we've got a link that's gone down. What happens is both these two switches will recognize that the link's gone down. It will then transmit a special packet to the master. The master will say, oh, link's gone down. So unblock the secondary port and data will flow. And this happens very, very quickly. The next feature is link aggregation. Again, very simple concept. It allows us to group a number of links together to form basically a super link. And what that allows us to do is allows us to provide greater bandwidth between two devices. So instead of having just one link running at 1 gig, you can have 5 ports running at 1 gig. So effectively, this is a 5 gig link. The added advantage of one of the additional advantages, as I say, of lag is it provides some redundancy. So if a link should fail, it's not the end of the world. You've still got connectivity over the other 4 links. Obviously, the bandwidth will drop down to 4 gigs, but you still got 4 gigs, and you still got network connectivity. So another feature, VLANs or virtual local area networks. Again, a very simple concept. It allows us to group it gets ports and puts them into groups. And these groups are called VLANs. And So we can see here, we've got in the first half of the switch, these ports belong to a group called VLAN 10. And in the second half of the switch, we've got a VLAN 20. And devices in a group, so in VLAN 10, when they transmit, they can only see other devices in their particular group, VLAN 10. And likewise, for devices in VLAN 20, they can only see devices in VLAN 20. So there's a couple of reasons why we probably want to do this. Sometimes you want to, create logical groups within your organization. So for instance, you could have a sales department or you could have a developers department. But also it reduces the broadcast domain. So, and we're talking about Ethernet here. So when a packet, a broadcast packet is sent out to the switch, this is a Ethernet packet with 4 Fs, that packet will be broadcast out all ports. And the end device has to then process that packet. So if you've got a very large broadcast domain and devices are all broadcasting, it means that devices can be, end devices can be very busy processing those packets. So by reducing the broadcast domain, we reduce the chattiness on the network. So, so VLANs are a layer 2 technology, and you can configure them on layer 2 switches. And the thing about it is devices cannot communicate to other devices in other VLANs. So to do that, what we need is a layer 3 device. And what the layer 3 device does is it takes these VLANs and gives these VLANs a network. So it puts them into a network. So this is an IP network. So in this case here, we've got a router up here. So the router is connected to both these VLANs. It gives both of the VLANs a network. And then once it's done that, it can then route between the two VLANs. So you can see in this example here, it's quite inefficient because if we wanted to go from sales to the SC department, it has to send up to the router and the router has to then send it back down. So it's a bit of a waste of bandwidth. So with a layer 3 switch, it can do it all internally. So it can create the VLANs, it can then assign the network to each of the VLANs, and then it will automatically route. So, so this is just talking about switching loops. So within a network, if you've got a loop, and we're talking about an Ethernet loop here. So if you've got an Ethernet loop, it's very, very bad because as long as you've got a loop in the network, an Ethernet packet will always exist. So it'll just keep getting looped around and around. So the thing that will happen is it'll bring down the network. Your network will be won't be able to function on it. And basically what happens is these broadcast packets will be looped around. And as you get more broadcasts, those broadcasts are sent out all ports, and then the devices hanging off those ports has to process those broadcasts. So if you're a PC, your CPU is quite grunty. So, you might notice a slowdown of your PC, but there's other devices in the network where, an excessive amount of broadcast will really, may crash the device. So these devices, could be like a wireless AP, or could be a CCTV, or could even be the switch. So there are a couple of technologies that can protect you against a loop from forming. One of these features is a loop guard feature. The other loop protection feature is spanning tree. So I won't talk about spanning tree, we'll just quickly talk about the loop guard feature. It's fairly easy, it's a fairly easy concept. So what the switch does is it sends out these LDF frames, loop detection frames. And if it receives the LDF frame back, it knows that there's a loop occurring in the network. And what it will do is it will shut down one of the ports. So there are a couple of scenarios where a loop can occur. So this first scenario here is you've got a cable connected back to the switch. In the second scenario, you've got an end device here and a loop is occurring on the end device. And in this third example here, you've got two end devices and a loop is created via these two end devices. So we can see what happens. So if a loop occurs with a cable connecting back into the same switch, the LDF packet will be received on one of the ports, and what will happen is one of the ports will be disabled. If we've got a loop occurring on a end device, so here, what will happen is the LDF packet will be sent out, it'll be looped around, it'll come back on the same port. In this case here, the switch will disable this port here. That means that the loop still occurs on this end device here. So that means, users they won't be able to access the network because the link is disabled. But also they may start going slow and whatnot just because there's a loop on the network. So active fiber monitoring, AMF, AFM. So it's a fairly simple concept. So the switches are, this is a feature on fiber optic cables. And what the switch is doing is monitoring the receive power. So if you're an organization and, security is a big thing, and you have the possibility of someone actually wanting to hack into your network via the fiber optic cable, what active fiber monitoring does is it monitors the receive power, and if the receive power reaches a certain threshold, it knows that someone's tampering with the fiber. So with fiber optics, if you start jiggling the cable and whatnot, the receive power will vary, it will change. So if the switch sort of detects that, it can then raise an alarm and disable the port. So typically, this guy here, so it's very hard, but it is possible to actually splice into the fiber and actually intercept the signal. Yeah, so this is what active fiber monitoring allows or stops someone doing. So PoE, power over Ethernet, another very simple concept. It allows us to provide power over data copper cable. And the reason why you want to do that sometimes is you'll deploy some end devices, in this case here, a wireless AP. Sometimes you'll be deploying these devices in hard to reach places, such as a roof or something like that, where power is not actually, it's very hard to get power. So through PoE, we can provide power to these devices. It also works quite well with CCTVs. A camera may be located in you want to get optimal coverage, and so it'll be located in a position where there just won't be power. So the standard's gone through a number of iterations. So initially, the amount of power that was provided over the data cable was 15.4 watts, and you had to use Cat5 cable. So Cat5 is the copper cable. So that's been around for decades. So the next iteration, PoE Plus, provided 30 watts of power, but you needed to have, or you need to have Cat5e cable. Typically not a problem these days because Cat5e cabling has been around for decades. And the latest iteration, PoE++, provides up to 90 watts of power. And again, you need to have Cat5e cable. So I just want to touch briefly on our autonomous management framework, AMF. So AMF is our management framework. And it's basically what it is a bunch of tools that helps you configure and manage the network. And it reduces your cost and resources when managing a network. So down here, we've got a couple of the features that you can, that AMF provide. So, you know, if you've got a switch that fails, you will need to replace that switch. And typically what you'll need to do is you need to load the config and you load the firmware onto the device, then swap it out with the failed device. With AMF, what you can do is you can just take the switch out of the box, plug it into the network, and what AMF will do is it will download the configuration and it will download the firmware to the device automatically. So it saves you a lot of time from having to configure and download the firmware to the device. So auto provisioning is similar, except for a device hasn't failed. You want to install a new device into the network. So what you do is you just program this port here to say, a new device is going to be plugged into it. So when you plug a device into it, so you just take it out of the box, cable it up, and what will happen is AMF will then program or configure the device and it will download the firmware to the device. So this third feature, centralized management, and this is actually quite powerful. It's just really powerful. It allows you to control multiple devices under one CLI command. So I'll give you an example. Say you've got, you want to deploy, you know, you bought a lot of CCTV cameras and you want to deploy them in a network. And you want to put them into one VLAN. So typically what you'd have to do is you'd have to log into this device, configure a VLAN on this device, configure a VLAN on, you know, then log out, log into this device, configure a VLAN on this device, so on and so on. So what centralized management allows us to do is you can log in to the CLI, and you can put all these devices into a group, and then you can just issue one command. So VLAN database, VLAN CCTV, and that VLAN will be created on all those devices at one time. So, you know, you can see the advantages. If you've got like 80 devices out there, it just requires one command. So AMF, you know, really saves you time and resources. So I just want to touch on network management. So network management is kind of a fuzzy term, because if you said, oh, I want to do some network management, it doesn't actually mean a lot. So there's a number of sort of subcategories in network management. You know, you can have, you know, network management can be, you know, fault identification. So if there's a problem on the network, we can, you know, use network management to work out where that problem is. Some of the other features of network management is like performance management. You know, you want to see how busy your network is. There's also network provisioning. So if you want to add new devices on or whatnot. Network maintenance is another part of network management. You know, you'll need to, you know, regularly update the firmware, and also you've got network security is another feature. So you want to know, who's logging into the network, are they allowed to log into the network, etc. So, so SNMP is a management protocol, and this it allows us to get information from our devices out in the network. So there are a number of components. So there's the SNMP agent, and these are your switches and whatnot. It could be your wireless APs, your CCTV cameras. And then you've got a centralized network manager down here. And then you've got the actual management protocol, which is SNMP. So what the SNMP manager does, or what SNMP allows you to do, is it allows you to poll these agents and pull back information. So it could pull back information, is the port down, how much traffic is going over a link, how is the fan, how fast is this fan spinning, or how busy the CPU is. We've also got, so these SNMP agents, they can not only respond to polls, but they can also send back information back to the SNMP manager. So in this case, here, it's called SNMP trap. So say if the device restarted, it could then send back a SNMP trap. And then what the SNMP manager does is it can then either notify, or you can see the results on a network management software, and it also can send an alarm. So Vista Manager actually is our network management tool. So it allows us to do a number of things. It allows us to do fault identification, performance management, network provisioning. So one of the things about Vista Manager is that it's the GUI for our AMF framework. So with AMF, it actually creates a view of the network. When you log into a device and it's running AMF, that device has got a view of all, how the network's put together. So what Vista Manager allows us to do is it allows us to actually see the topology of the network in a graphical format. We've got a couple of plugins to Vista Manager, so the AWC controller. So through the AWC controller, we can actually control our wireless APs, and it's also got an SNMP manager, so we can actually use this SNMP protocol to poll devices for information. So just a couple of screenshots of what it can do. So Vista Manager, automatically creates a map of the network. So you don't have to do anything. You don't have to grab an icon, put it on the map, and then draw a link. It does it automatically. You can see down here, and then it also draws the link speeds. And you can group these into particular areas, so you could have buildings and floors, etc. Down here, we've got traffic visualization. So this is actually quite useful. I don't know if you've ever heard the term network weather map, but what it allows us to do is it allows us to view the network and see the performance of the network. So it actually sees how busy the links are. So this is really good for performance performance management. So it's got a historic view, so you can look back in time. So for instance, you could have a look at this link here and note, maybe like a year ago it was running at maybe 20%. And then you log in and you go, these days it's running at 50%. So you could say, okay, based on this growth, maybe in a year or 2 years' time, we need to upgrade this link. And you can provision that, you can budget it. And when the link becomes at 80%, you can then say, okay, we need to upgrade it. With Vista Manager, we can have a look at VLANs, see how they're configured on each of the devices. And also we can have a look at route management. So we can actually see response times, how fast are the packets going through the network, and are there any bottlenecks? So that's that. So products for Ring and Star network. So I probably won't go through this. It's probably best if you talk to your country office, because it really depends on what your requirements are. But within, a Star or Ring topology, you've got your core distribution edge, and we've got specific switches that should be used in those situations. And then we've got a bunch of routers. So, so thank you, and I'll now hand you back to Aki-san.
Okay, thank you guys for your presentation. Before we move to Q&A session, I'd like to ask for the survey. As you can see on the screen, you can see the QR code. So we would like to improve our service. So we'd like to listen to your voice. So could you please help for the survey? You can just scan the QR code in the slide. And then please fill in. Please fill in the survey. And if you cannot scan the QR code, no problem. Tomorrow you will get the email asking for the survey. So please click the URL in the email. You can fill in the survey. So thank you very much. And this is the end of the slide. And we have now 5 customers raised their hands. So Q&A session will take some time. So if you'd like to leave this webinar, you can leave now, because usually Q&A session will take some time. So this is the end of the presentation. So you can leave the webinar now. Thank you for your time.